Welcome everyone. So this is our 58th live stream geometry, and we have 6 other people here with us already. So today I'm going to take 2 problems that were suggested to me from the participants of this channel, and they were given to me on Discord, and the rest of them I'm going to take from the Saudi Arabia team selection test, but for the Gulf Math Olympiad. So I think last time I did the selection test for the IMO, but this time I'm going to do the Saudi Arabia team selection test for the Gulf Math Olympiad. So if you want to join future sessions and solve the problems with us, you can email me at mgreenb801@gmail.com. That's my email's in the description of the video, and the sessions are at 8 a.m. US Central Time. So with that, I'm going to share my screen. So hold on just a second. All right. Okay. So this problem, this is one of the 2 suggested problems. This is from the BMO Balkan Math Olympiad shortlist. So we have a triangle ABC. BC is greater than AC. So let me see how I want to do this. I think I want C to be at the top.
Actually, I did this before, so maybe.
Oh, really?
Can we go on?
Yeah. We could do the next. Start with the second one. So this one. So Stefan sent me this one. So we have a cyclic hexagon. But what I'm going to do. So. Let's see. So the diagonals, we have AB is parallel to CF. So we have A, B, C, D, E, F. But what we could do is we could first start out by drawing AB, and then we could draw the parallel through C to AB. Whoops. And this will be point F. And then D and E will be 2 of the other points. And okay, D and E, DE and CF. Okay, so basically, I think we need so this should be S. So AD, CF, and BE intersect at S. So we have something like this. DE and DE and CF intersect at M. So let's see if we can make that a little bit closer. Kind of like that, maybe. And N is a point such that M is the midpoint of SN. So basically we reflect S over M. So this should be N. And we want to show the circumcircle of ABN passes through the midpoint of CF. So I'm gonna rewrite that. I'm gonna say let's label the midpoint of CF. Let's call it G. So we want to show that AGBN is cyclic. All right. Let me check that that's true, and then I will make it look nicer. All right, so we have that and this. I probably don't need to draw all the sides of the hexagon. So yeah, I guess we just kind of have to remember that M is the midpoint of Sn. And then we want to show AGDN is cyclic. So maybe I'll draw some of the sides of AGDN. I want to show that that's cyclic. So since M is the midpoint of Sn, I don't know if there's something we can use with harmonic conjugation.
Okay, so if we could prove that Sg times Sn is equal to Sa times Sd, which is equal to Sc times Sf. So we solve the problem, right?
Oh yeah, because Sa times Sd, it's Sf times Sc. So if we could show that's the same as Sg times Sn, then that would help. Yeah,
and because G is the midpoint of CF, which means we must have FCSN is a harmonic conjugation. Yeah.
FCSN.
Yeah.
Okay. So how okay, it's suffices to show that FCS and N are in harmonic conjugation.
Yeah, we need to prove it. And because M is the midpoint of Sn, we just need to prove that Ms is equal to MC times Mf.
Or Ms squared is MC times Mf, right?
Yeah. Which is equal to MD times ME. Yeah, and we need to triangle MSD and MES is similar. Yeah, and we can use angle chase. Yeah.
Okay, so that's probably angle chase because this angle is half the sum of these two arcs, angle ESD, and angle MSME is half the difference of FE and CD, and so that probably solves it. Okay, so I'm going to write that up. We solved that really fast. Did Khan have a different solution? So we used a little bit of an angle chase, but oh, he's just saying that would solve it. Okay, so basically, so first I'm going to show angle ESD is equal to angle SME. So yeah, okay, so ES, so I'll write it out like this. Angle ESD is equal to half of arc AB plus arc DE. And then we also have angle SME. It's equal to arc FE minus arc CB. And so we want to show those are equal. I'll say EF. So basically we want to show those are equal, and that's probably just angle chasing, because then we want to show AB plus DE plus CB is EF. Is that true? Maybe I might have done something wrong. Let's see. So that's half of the sum of those two, and this is half of that minus that. So AB, so BE plus CD is CE. Did I show the right two angles? I want to show. Oh no, I need to show MSD as SEM. Okay, I did the wrong angles actually. So let me just start over here. So we have SEM is half of arc BB. And then, yeah, okay, I got this. So and then we have DSM is half of arc AF plus arc CB, which is half of BC plus CD. Which is half of arc BB, which is angle SEM. So angle DSM is equal to angle SEM. Let me break this up. So that means triangle MSD is similar to, let's see if this works. All right, so we have another person joining us. Okay, so this means that triangle MSD is similar to MES. All right. And once we know that, then we have MS squared is MB times ME, which is MC times MF. And if MS squared is MC times MF, then by that well-known fact, so we've used it on this channel a lot, but if that's true, then since M is the midpoint of Sn, that means N, CF, S, and N are in harmonic conjugation. So and then once we know that, so how does that show that ADGN is six? Oh, by power of a point, because then we have GS, since they're in harmonic conjugation, then GS times, it's like you use the same so GS times GN is GC squared. I'm trying to remember how to do this. So we want to find GS times SN, right? So we have AS times SD, is SC times SF. And we want to show that that's SG times SN. Oh, I guess that's just the same theorem. Yeah. Okay. So like since G is the midpoint of CF, then SG times SN is SC times SF times SC. So that's using that well-known fact, but it's like using it in a little bit different way. So like, so SG times SN is SF times SC. Which is SA times ST. So actually I'm going to start by saying let G be the midpoint of CF for FC. So then we have ABGN this means that ABGN is cyclic. So AGBN is cyclic, implies that the circle ABN passes through the midpoint of CF. All right, that was a nice one. Let me check the chat. Okay, so there's a solution that doesn't use projective geometry. So maybe if you guys find it, you can post it on Discord. But yeah, it looks like an interesting problem. So I'm going to move on to the next one. Yeah, this one doesn't look super hard, but let's see. So we have a triangle ABC inscribed in a circle, and I is the midpoint of BC. And H and K are the projections of I on AB and AC. And then we draw the circumcircles of those two. So, so this is H, and this is K. And then we draw the circumcircles of ABH, ABK, and ACH. And we want to show that BC is 4 times the distance between the centers of these circles. So that's one center, that's the other center. Let me hide a few things. So we want to show BC is equal to 4DE. It almost looks like DE is parallel to BC. Is that actually true? I actually don't think it is true, but I'm not positive. Oh, it looks
like it is.
Yeah, it looks like it's true. Okay, that might make it a little easy then. Well, I wonder if that's obvious because the distance from D to BI, well, actually now I'm not sure if it's that obvious. Let's see. I wonder if this is like the median. Yeah, we don't even need the circle O really. But I wonder.
Can you draw the altitude?
Yeah. Oh yeah, it looks like it passes through the altitude.
Other ones also.
Okay. Yeah, that is interesting. So yeah, DE is parallel to BC. Is that obvious?
If you prove that A altitude is the radical axis, then it solves.
That would solve it. Okay.
Yeah, maybe we can use now POP by naming intersection of the circle of ABK with BC.
Oh, like just name that point.
Yeah, and the other one.
Or I was thinking we could name the altitude, the foot of the altitude, and then show it has the same power.
Yeah.
Yeah. I think that might be what you're saying. So
it seems that HLIK is cyclic, but I don't know how to prove it, or I don't know if it is needed for this problem.
okay.
It's obvious from 90 degrees.
Oh yeah, they're all right angles. AHI is AKI is ALI is 90.
Oh, okay.
That's an interesting observation.
Michael, can you check for me that if J is the midpoint of BL and G is midpoint of LC?
Oh yeah, it looks like it. Yeah, yeah, it's definitely true.
If we prove that, we are done with radical axis.
Okay.
It must be the midpoint. Just from the PowerPoint, CI times CL is equal to CK times CA, right? And
yeah.
CA times CK is equal to CB times CG.
Mm-hmm.
And CB is twice of CI, so CL must be twice of CG.
Ah, interesting. Okay. And then Serdar, you said that solves it.
Yeah, easily by power of point.
Because that means that
LB times LG equals to LB times LC over 2. Then it's symmetric.
Yeah, okay. All right, so I'm gonna write it up.
So all that's just to prove that DE is parallel to BC, right?
Yeah, so let's see. So we showed that AF is the altitude. Like we showed that, yeah, AF is perpendicular to BC. So yeah, actually I'm gonna hide this line because really, like we're gonna show AL and F are collinear because L is the same. If L is, so yeah, let me just draw this. So once we know that, how do we show DE? I think we might be able to use Casey's theorem, right?
It's radical axis.
Yeah. So because LJ times LC is equal to a half of LB times LC, which is LB times LG. So L line the radical axis of two circles. So A, L, and F are collinear, which means that DE perpendicular to AL, which is DE parallel to BC.
Okay, so then then we know DE is parallel to BC. That's a good point. So yeah, I realized the part where AL and F had to be collinear, but I forgot. Yeah, from that it's obvious that DE is parallel to BC. Okay. And then
B and E are the centers, and AF is the radical axis.
yeah, so we know DE is parallel to BC because of that reason. And then how do we show BC is 4 times it?
Could you draw the diameter of two circles? That AD and AE cut to, yes.
Yeah.
Yeah, and both of them should be collinear with F.
FM and N.
Yeah.
What have we proved till now? I didn't follow.
So I'll write it up. So first, I'll say let L be the foot of the altitude from A to BC. And so then we have angle AHI is ALI is AKI is 90. So and so that means that AHLIK is cyclic. And then we let the circles, so let let the two circles intersect BC at G and J. So let ABK and ACH intersect BC at G and J. And then there we go. So then we have CG times CB is CK times CA. Which is equal to CI times CJ, which is equal to CB over 2 times CJ. And so, did I do that right? So CJ, oh no, I have to use L somewhere. CK times CA is CI times CL. So that means that G is the midpoint of CL. Similarly, J is the midpoint of BL. And then that means L has the same, we can show easily that L has the same power with respect to both circles, because then we have LJ times LC is equal to BL over 2 times 2 GL, which is equal to BL times GL. So that means that L lies on the radical axis of those circles. So A, L, and F are collinear. Okay, so we proved all that. Now,
Michael?
yes.
So I think if we can prove that IJ is equal to GC, then we are done.
Okay. Hold on just a sec. So, okay, so you want to show IJ is equal to GC?
It is obvious because J is the midpoint of BL. So IJ is yeah, just use calculate. So IJ will be equal to GC.
Yeah.
Okay, so if we can prove, if we can calculate that, then EI must be equal to EG by symmetric.
EI or
EI, yeah, the center of the circle, EI must be equal to EG.
EI has to be equal to EG by symmetry.
Yeah, because IJ equals JC, equal GC, and EJ equals EC. So maybe by symmetry or by equal triangles.
Okay.
So next we'll draw the diameter of the circle ADK. Diameter B, like the reflection of B over D. Can you draw the reflection of B over D?
Yes. One sec. B
over D.
Michael.
Mm-hmm.
So if D is fourth of BC, so we should prove that MN is half of BC, right?
Mm-hmm. Yes. And maybe is that easy to just see that this is a parallelogram right here? Because actually, are Ki and M collinear? Yeah, they are, right? Ki and M are collinear. Yeah, this might be easy to see. So that has to be collinear, and this also has to be collinear, right? And once we know that, it's probably easy to show there's a parallelogram, right?
Oh, I'll just finish my point, right? Can I just finish my point?
Yeah, sure.
So can you connect B prime?
Yes.
And B prime G. Let's see. So we have D is parallel to BC. And D is the midpoint of the side BB prime. So DE must be the midline of triangle BB prime G, which means EB prime must be equal to EG.
So DE is the midline of BB prime I. Is that what you were saying?
BB prime G.
Oh, yeah. The line DE. Yeah, so the line DE is the midline of that triangle.
So EB prime is equal to EG. Can you connect those segments?
DG or EG? Sorry.
Like DE is the perpendicular bisector of B prime G.
Oh yeah. So yeah, DE is the perpendicular bisector of B prime G.
Since it passes through the midpoint of a segment and it is parallel to the other side.
Mm-hmm.
So
Yeah.
that implies that EB prime must be equal to EG.
So sorry, say that one more time. BE prime is equal to EG. I think that's what you were saying, right? BE prime equals EG.
Yeah, exactly. Those two. Can you connect them?
Mm-hmm. So sorry, let me connect it. And then from there,
since we proved that EG is also equal to EI, so E is the center of is the circumcenter of triangle IGB prime. However, B prime GI is a right triangle.
Yeah.
So that means E is the midpoint of B prime I.
So EB is half of BI, and that would solve the problem. So really, we have two ways to finish it. Both of them look pretty.
I think the way that use the parallelogram is more like elegant than mine.
Interesting. All right, I'll just leave that on the diagram just because I think it's interesting. But let AM and AN be the diameters of the two circles. Okay, so I'm going to write up, the other one. So let AM and AN be diameters of ABK ACH, and then it's KI and M. So we have angle AKI is 90. Means that KI and M are collinear. And then similarly, HI and N are collinear. And it's not hard to show that. Well, yeah. So first of all, we know that DE is parallel to BC after this step. So let me fix some of this stuff. So I don't think I need to explain that stuff. So so MN, so since basically AD equals DM and AE, so first I'm going to show that MICN is a parallelogram. So since MI is perpendicular to AC and NC is perpendicular to AC, then that means that MICN is a parallelogram. And then that means, so I'm running out of room here, but we'll just move that up a little bit. So then we have MN is parallel to BC is parallel to DE. Well, actually, we probably knew. I mean, we knew that MN. Do we even need that it's a parallelogram? Yeah, because we need MN is equal to IC. Yeah, so we have BC equals 2IC equals 2MN, which is equal to 4DE. All right, that was a fun one. So yeah, these problems are a little bit easier. Maybe I could look up some harder problems after. Let me check the chat. Yeah, okay, so Serdar, after proving EI is equal to EG, yeah, Serdar kind of had another way of doing it, which is the way that Wynn just said. All right, so I am going to move on to the next problem. Yeah, it's only 9:42, so yeah, those problems are a little bit easier. Let's see if this one's harder. So this one looks like, I'm not sure how hard this one is. So we have a circle and we have 2 tangent lines to it, CS and CT. So that's C, and then we draw the tangents to it. So this should be O. You might want to hide this point. Or I'll just call it like K. So CS and CT are the tangents. So CST is the polar of C. And maybe we'll use harmonic quadrilaterals or something here. So we want M to be the midpoint of minor arc AB. So A and B, I guess, can be any points. That's kind of weird. I don't know if it's okay if A and B are like that. So let's see, I'm gonna draw the perpendicular bisector of AB. And so M, it should be the midpoint of this arc. So this is M. And we want to see where MS and MT intersect AB. Yeah, this definitely looks like it's going to use projective geometry. So maybe I'll move A and B apart a little bit, something like that. So MS intersects it at E, and MT intersects it at F. And then X is on OS, and Y is on OT. This is kind of interesting. So basically we draw the perpendiculars to AB at E and F. And we see where they meet OS and OT. That's weird, but okay. And we want to show X, Y, and CM are perpendicular. So this is X, and that's Y. This looks like a good problem, actually. All right, so let me see, try to make the best diagram that I can. I kind of like that a little bit, and then I can make it maybe a little bigger. So like that. It's an interesting problem.
SEFT is cyclic. That is not hard to see.
Okay, is that power of just an angle chase, probably, right?
You can do angle chase, but it is easier to do power of mind.
Okay. Yeah, because angle TFB, it's half of arc TB plus arc AM, which is half of arc TB plus BM, which, so yeah, I see the angle chase, and then the power of a point. And we have ME times MS. Is that MA squared?
Yeah.
Yeah, so that's how you would do it that way. Okay. So I will draw that. So we have SEFT is cyclic.
Wait, can you check that if the problem is right? Because I think in my diagram it isn't right.
Yeah, let's little X, Y. Let's see.
You move point A, B, M around a little bit.
I think it's right. Let's see. Let me draw this point in. Whoops. Yeah, I think it's true. Yeah.
Sorry, Michael. Is that a triangle HE and YTF isosceles triangle? And
SDM and what? And sorry.
SES.
SEF.
SES. Yeah. SES. Maybe you can try
SES X.
Oh,
SEX.
SEX and YTF. Ah, okay.
Yeah. And it's just to you can make some circle because SY is the line pass through maybe two circle maybe.
Okay, so basically we have this circle. Whoops. Center X. And then we have this other circle with center Y.
Yeah.
And okay, so basically we want to show CM as the radical axis of those two circles.
Oh, that is actually very easy.
Yeah.
Because
yeah?
CT squared is equal to CS squared.
Okay, so then that's also
quite obvious.
Yeah.
all right. So we have just solved it. So first we use an angle chase to show SXE and TYF, or SX is XE. So oh, it's all right. So angle XES, that's 90 minus SEA, which is half of the sum of those two arcs. Okay, so yeah, I know how to find this angle right here. I'm just thinking, how do we find this angle? So this angle, okay, so yeah, I see how to do it. So angle XES is 90 minus angle SEA, which is 90 minus arc SA plus M SA plus MB. Which is yeah, copy paste doesn't work so well within the text box, so I usually retype everything. So SA plus which is 90 minus half of SM. Oh, I need to do that. So that's XES, then XSE is OSM, which is so yeah, OSM is 90 minus half of SOM. So yeah, so this is 90 minus half of angle SOM. Which is angle OSM. Which is angle XSE. So I'm not sure if this is the shortest way to do it, but it still works. So XS is equal to XE, and similarly, YT is equal to YF. So now since CS squared is equal to CT squared, so it's also easier to see that both of those circles are tangent to the bigger circle. So the circle center, the circle, I'll just give it a name. With center X through S and E is tangent to the circle O. And then the same is true with the other circle omega 2. That's easy to see. So then oops. I forgot the backslash. So CS squared equals CT squared implies C is on the radical axis of those two circles, and also And then M is on the radical axis by the radical axis theorem. So yeah, because we did need to use that S, E, F, and T are cyclic, I think, right?
No, we didn't.
Oh, we didn't need to use it. So how did we show? So I see that C lies on the radical axis of those two. How do we show that M lies on it?
Because ME times MS is equal to MF times MT.
So we did need to use that as cyclic then.
We actually didn't need to use that it is cyclic because we proved that it is cyclic using that.
Using that. Okay.
We don't need to prove it's cyclic, just need to say that CE times CS is equal to C. Oh no, SE no. That point ME times MS is equal to MB square, which is equal to MF times MT.
Okay.
Yeah, so M lie on the radical axis.
So okay, so we have ME times MC is equal to MA squared, which is equal to MF times, oh, this should be S, MF times MT. So M lies on the, I'll just say that implies CM is the radical axis, omega 1 and omega 2. And that means that CM is perpendicular to XY. See if this works. Okay. And yeah, this is obviously true. All right, because angle MAB equals angle MBA equals angle MSA. So yeah, that solves that. All right. Here is the next one. It's only 10 and we're already almost through them. So yeah, let's see how hard this one is. I like doing a couple easy ones. Then we could, the second half, we could do harder problems. So ABC, D and E are the midpoints of AB and AC. D and E, and then we draw, oh, this looks kind of similar. Well, not exactly. So we have ABE and ADC intersect at K. This feels a little like symmedians. Is AK a symmedian? I wonder if we've done this.
Yeah, I think it is. I think it's a familiar property, I think.
Of the symmedian.
Yeah, I'm just, yeah, I remember it is true. Hey, we just prove it later.
Okay, yeah. So yeah, that might make this problem really easy actually. Let's see. So the line LB, so this is point L. And then it says LB meets that circle at M. Almost looks tangent. And LC meets it at M. Something like that. And okay, so we want to show K is we ultimately want to show K is the midpoint of MN. Okay, let me draw O.
AK is without a doubt a semedian because if part B would be true, then it would prove that it would be a semedian.
Okay. So and the is the converse also the case? So if you knew AK is a semedian, does that prove part A?
Not sure.
Okay. Let's check the chat.
MKN is collinear due to an angle change.
Because we can show that those angles add up to, yeah, because, yeah, so it's kind of trivial that they're collinear. Then
Yeah, I saw that just a minute ago.
Now,
or you can use the inversion LK times LA.
So LK times LA, that's LM times LB, which is LN times LC. So yeah, we know BMNC is cyclic.
Yeah, so because after the inversion, LACB is cyclic.
So we kind of know by LACB is cyclic by definition, right?
Yeah. So MB transfer to M, A transfer to K, C transfer to N. So MKN must be collinear.
Okay, so yeah, you thought about it by inversion.
Yeah, and because the line MKN transfer to the circle BAC, and LO is the diameter, so LO must be perpendicular to MN.
Okay, that makes sense. Because yeah, the circle BAC maps to MKN when you invert about L.
Actually, we can just use like opposite oriented similar triangles. Like we have LMN and LCD are similar, and LO is the line connecting point L and the circumcircle of LBC. So it must be orthogonal with the altitude drawn from L to BC.
So LO must be orthogonal with the altitude from L to BC because
that's just the property of orthogonal lines.
Okay. Well, so I get like MN and BC are like anti-parallel with respect to L, right?
Yeah.
So, but I don't see how that shows.
So I'll just make it clear. Can you draw the altitude from L to BC?
Yeah.
And label that point, let's see, P.
Okay.
So we have LP and LO are orthogonal lines, right?
LP and LO. Well, so is it?
Yeah,
Oh,
LP,
because that's just true. Because if you look at triangle LBC, the altitude is always isogonal to the line joining the center.
That was what I'm talking about. Yeah.
Yeah. Yeah, I see what you're saying. So since BC and MN are NP parallel,
Yeah.
then
all perpendicular to them.
that makes sense. So yeah, there we go. We have two proofs. All right. So that shows. I'm just going to make P a little bit farther away. So, okay, so we showed that MK and N are collinear. And then.
Oh, yeah, and part B isn't really hard too.
Okay.
Yeah, just present part B and we'll, speed running the problems.
Yeah. Sounds good.
So you draw the line through L and parallel to MN.
Okay, parallel or perpendicular?
Parallel. We're using harmonic conjugation to prove that K is the midpoint.
Okay.
You just like take an arbitrary point on that line to just easier to call it out.
Yeah.
Okay, so we need to prove that LF, LK, LB, and LN is a harmonic bundle, right?
Mm-hmm.
Then it will finish the proof.
Yeah.
So we have MN and BC are anti-parallel, right? And we have LF is parallel to MN. So it can be easily proven by an angle chase that LF is the tangent line to the circle O.
Yeah. So
LA is also the C-median line of triangle BLC, so it must be a harmonic bundle.
that makes sense. Yeah. All right. So I'm going to start typing it up. I wonder if there's another way, because KM over AB has to equal yeah, but I think that's the simplest way to do it. Is just using the harmonic quadrilateral. So okay. So first of all, yeah, we could use either inversion or we could use the other way. I mean, both of them work. So I'm gonna do it the way that you said most recently, but yeah, they both work. So, oh yeah, KM over KL is AB over BL, which is AC over CL. Oh yeah. So yeah, both those work. So we have angle MKA. So first of all, I'll say that line AL is the semedian of triangle ABC, and that's kind of well known. So that's well known from, and it's also in previous videos. So then angle MK, so we have angle MKA is 180 minus ABL. Which is equal to angle ACN, which is equal to angle AKM. So actually, we just went in a circle, but ACN is 180 minus AKN. So that means MK and N are collinear. And then once we know that, we have LM times LB is LK times LA, which is LN times LC. And that means that BM and C is cyclic. And so, first of all, we have LO is what do you call it? Isogonal with LP. To LP with respect to angle BLC. That's an easy angle chase. And also we have BC and MN are anti-parallel. So basically the angle between MN and LO, so I write it like this. So the angle between MN and LO is equal to the angle between BC and LP, which is 90. So, and then to show K is the midpoint, I'm just going to copy the calculation from the chat. So, so we're using that ABCL as harmonic. So I'm going to write right here that ABLC is harmonic. And that means that AB over BL is AC over CL. All right, let's move on to the next one. And then, did someone put in the chat like another problem we could do that might be, oh yeah, the Gulf Math Olympiad one. So yeah, the first problem I suggested, so Serdar said he had done this one. He's not on anymore, so maybe we could do this after I finish